Great. Hello, everyone. And thank you for sticking around. This is a very interesting panel. So if you guys are developers or very interested about how the tech behind DCC actually works, stay in the room and get some coffee to ask great questions. So let me introduce the panelists. We have Yannik here, CEO of Arcium, focusing on MPC, or the MPC experts on the panel here today. Can I get this off? And maybe we can also move to... Yes, big applause, please. Come on. Then we have Supdoggie, who already gave a nice presentation today. He's lead dev at SilentSwap. And now I forgot the other... founder of Starshell. Thank you so much. And he's the expert on FHENT on this panel. Big applause. And then we have Karel, who's co-founder of Union, and he will be supporting ZK on this panel discussion. Perfect. Cool. We all have enough space. Yeah. And cheers with the beer already here on stage. So, guys, as I said, this is a more technical panel. We had a great overview already on now just touching a bit on regulations, also talk more about use cases later on. We really want to discuss the different cryptographic mechanisms that DCC are actually based on. We just had a great transition in the previous panel. They talked already about how these technologies should work together, and this is what we really want to dive deep on here today. My name is Zoe. I got introduced already, VP of Growth at Phala. We are a TE-based coprocessor, so I will be also supporting TEs on this panel where needed. But it can be also become a discussion where we don't agree necessarily, right? Because some people have very strong opinions about what kind of cryptographic mechanism is maybe better for specific use cases. So before we get started, maybe you guys can summarize or introduce really the product that you're building and what problem you're solving in 1 minute. So the guys have an overview of what your expertise relies on. Karel.
Of course. So at Union, we do zero-knowledge-based cryptography to support our interoperability network. So what that means is generate proofs to secure asset transfers between different blockchains. And that means that we need to really focus on the security aspect, because if you manage to crack this once, you can empty all of the vaults and get all of the assets that are locked. So in this case, we're really looking for kind of a permanent security level, as well as censorship resistance. So we don't want to rely on oracles, multi-sigs, or specific companies to provide the security, because we want to be able to facilitate asset transfers to any blockchain, for example, privacy blockchains as well, which means that you want a truly decentralized product.
And just to add, for the interoperability, you use IBC, right?
Yeah. So we're IBC compatible, which is originally a protocol that came from the Cosmos ecosystem. It's used by Celestia, Initia, and that we've now brought to, I think, 10 other ecosystems.
Great to have you. Supdoggie, if you want to summarize in 1 minute what problem you're solving. I mean, you gave a great presentation already, but for anyone that just joined the room.
So I'm actually representing a few different things here today. So there's the Starshell side of things, where I am doing research and development on secret networks specifically. I'm also a lead developer of the SilentSwap platform, which is, as we announced earlier today, we just launched public whitelist beta for. And but in terms of specifically this talk today, yes, it's mostly trusted execution environments. Of course, everything relies on the privacy provided by secret network contracts, confidential computing on secret network. But the SilentSwap platform is also using bridges that depend on MPC. So it is actually multifaceted. No ZK yet, but yeah, I mean, we rely on MPC and trusted execution environments to provide privacy for users to be able to basically obfuscate or anonymize their swaps from one chain to another, to escape a bit of the whether their address has been doxed, and it is a privacy solution that strikes a certain trade-off, and we believe that this use case fits the way that we're using those crypto technologies.
Perfect. So one specific use case already for this cryptographic mechanism.
Yes.
Yeah. Yannik, 1 minute summary what problem you're solving.
So with Arcium, we are building generalized confidential computing powered by secure multi-party computation. And so what that means on a technological level is that within Arcium, which is a purely computational network that can be accessed from different ledgers to have confidential on-chain applications or even off-chain applications. We have different MPC protocols as backends. We try to optimize for the lowest possible trust assumptions with a scalable trust model. So what that means is that we have the dishonest majority trust assumption in our protocols. And we adapted protocols to also introduce decentralized accountability. So cryptographic misbehavior can be identified and then can be punished with a staking and slashing mechanism. And our protocols are heavily optimized and made trustless. So we support, for example, a backend that allows for very efficient tensor operations. So it's possible to build machine learning applications that don't require any trusted intermediary, don't require any trusted supply chains, just peer-to-peer in the Arcium network.
Great. Also, one specific use case more towards machine learning, AI use cases.
I would rather put it this way, that we have different backends. So we have a backend that protocol that's really tailored for just integer operations, and then we have a backend for those tensor and real number operations, right? And by allowing Arcium essentially to switch between those backends as well, we can be generalized by having specialized backends in the network.
Great. Okay, very cool approach. So just to summarize, right, DCC, decentralized confidential compute, can be executed by different mechanisms, as we just learned. Multi-party computation, zero knowledge, or trusted execution environments, or fully homomorphic encryption, or a great combination of everything that we also want to discuss today. But since we have really strong opinions here, and Karel, I know you are the heavy promoter of ZK, maybe you can summarize for the audience why ZK is a great cryptographic mechanism for you, for the use case that you want to solve, but maybe also give a bit of the light of the weaknesses, right, and how you maybe overcome these challenges with building your product.
Yeah, I would say ZK is almost the perfect technology. At the moment, really, the only weakness is performance, and what we've seen already this year is kind of an approximate 10x performance for most ZK stacks. With that, as an engineer, I really don't see a need for other tech stacks if you can just plug in kind of the magic all-secure ZK black box to do your verifiable compute or confidential compute. Now, for highly secure systems, I would say it is actually always good to have multiple different technologies. Just because we might have like the theoretical security of something, there's of course still the potential for programmer error, right? And simply implementing something twice or having another tech stack just allows you to reduce that programmer error risk overall. On the ZK side itself, the great thing is that it aligns much better with what we're trying to achieve in crypto as a whole, right? We're trying to reduce dependencies on kind of the real world and make products that operate in this perfect platonic code-only universe, right? Where we have these beautiful DeFi protocols and objects, and we don't actually work with entities. And as you start kind of traversing the different hardware solutions that you could do, what you keep encountering, to me at least, what I keep seeing, is different leaks that we then plug up with more tech, like open sourcing these, and then having like multiple authorities, and then combining all of them again, and maybe aggregating those. And the complexity stack just keeps on increasing. This makes sense if ZK doesn't work, right? If it's too expensive to do. But with potentially one more 10x performance increase on the ZK stack, I think we'll kind of see what we see with optimistic rollups as well, that they actually have a very short amount of time that they were really viable, never potentially like reach the state where fraud proofs worked before they transitioned to just becoming ZK rollups, right? And ZK winning in the end.
That's interesting. I have directly follow-up question, but Yannik, I would like to hear your approach. Are you supporting this opinion, the strong opinion, ZK is the best?
I'm a fan of ZK, zero knowledge proofs, but the problem with zero knowledge proofs really is that you're not able to operate over shared encrypted state, right? So ZK on its own really is this two-player setting with a prover that generates a zero knowledge proof, operating over some sensitive information, not exposing that sensitive information, if you're talking about confidentiality and privacy, and submitting this proof to a second party, which in most cases is just a distributed ledger that can verify this proof, right? That is very powerful, but only addresses a subset of operations that need to be performed. And confidential computing really is being able to execute whatever computation over arbitrary state without requiring some specific players to hold secrets exclusively, right? So it's about autonomous execution, and for that we require, or we utilize, I mean, there's different technologies you can use, but for us it's multi-party computation, right? And that, in this case, when thinking about ZK, about verifiability, verifiable compute, can also be leveraged and combined to a multi-prover setting, right? So you can combine MPC and ZK to produce ZK snarks or starks with multiple provers holding secrets. And so for us, because we want to allow arbitrary encrypted data to be processed without anyone having to decrypt it, without requiring trust in a specific single party, we utilize MPC combined with threshold encryption. And that allows a set of nodes to process computations without any individual seeing the data, as long as not all of those nodes are malicious. That's the trust assumption that we are working with. Our trust assumption is there's one honest player that's not maliciously collaborating with all the others. And that makes MPC very powerful because we can operate with this dishonest majority trust assumption. And on top of that, the great benefit of using MPC really is performance. And so the protocols that we are working with are so-called protocols in the pre-processing model. That's essentially what differentiates those protocols from fully homomorphic encryption. So we operate with somewhat homomorphic encryption, taking a subset of efficient operations essentially, and for other operations, utilizing a so-called pre-processing phase by splitting the computation into multiple phases. And that's why we believe essentially that this is really the answer for confidential computing, because for one, we have this scalable trust assumption that can scale arbitrarily. We can make use of hardware optimizations for all homomorphic operations that we have. And further, we have new protocols that also allow to reduce communication overhead, which still is the limiting factor for multi-party computation, but there have been amazing breakthroughs on that front as well. So I think scalability and trust model-wise, yeah, that's why MPC.
Yeah, I just want to adjust my answer. Like at Union, we only need to verify computation. There's no confidentiality. If you need confidentiality as well, then MPC is still pretty great.
Great. Then good addition. Supdoggie, from FHE and TE approach, right? How would you compare it to what Yannik and Karel just explained?
Well, I think there is in both of these contexts, I think the computation is happening on the node side. In ZK, you actually do need an active client to do quite a bit of heavy lifting. With trusted execution environments, you can actually you can get away with using edge devices because the encryption is very simple. You could run edge, even on like a Raspberry Pi, you could interact with secret network. The client has very little to do. The trusted execution environment is doing all the heavy lifting. It's different than an MPC setup because in an MPC setup, you're really just relying on these party of nodes to do things. Not saying that a Raspberry Pi couldn't contribute. I'm not sure what the computational requirements are in this case, but it is.
The setup for us at Arcium would be similar. You outsourcing to the network, so not having to be an active participant,
right,
but would be possible.
Yes, yeah. Also, FHE does not meet this requirement either. So, this is, I think, one place where trusted execution environments will always excel is that it has a very low cost for client to be able to engage with the network and reap the benefits of confidential computing because they have a very specific thing they need to do. They just need to encrypt their inputs and decrypt the outputs.
Yeah, great. And then bringing this back to the ZK approach, right? Because trusted execution environments, ZK actually as well is a quite old cryptographic mechanism, but TEs are used in Web2 use cases for military, governmental security, right? So my question is now, because you said like ZK is the solution for everything, we don't even need TE, but we would need to secure the tech stack more. How use case ready are we with this? Because TEs are ready to use and can be integrated in the blockchain and Web3 use cases, right? For ZK, what you just described, it feels like there's still some more time to go to actually have the scalability and the lower cost as we have in TEs. How would you comment?
Yeah, I think right now, for example, look at proving the entire Ethereum L1 consensus, that would approximately be about $1 million a year, which to me, with what we're spending on economic security for most chains, is already more than low enough to make this viable, actually extremely cheap to switch to this. So that means that you only really need economic security for consensus and not for execution anymore. With regards to how ready is ZK, I actually think it's extremely ready and very applicable in a lot of situations. Now, for the military, right, their use case with TEs is it's an additional layer. But in military devices, already the attacker doesn't have access to the device itself, right? Like their servers are not in public data centers. There's a guy with a gun in front of the actual physical hardware protecting it. In the case of blockchains, right, we don't know who actually manages the hardware. Usually it's Hetzner. I think most nodes went on there. But in essence, like we want to have a system where like we don't need to monitor the physical hardware itself. And so then the extra guarantee that TEs give, I think, isn't strong enough to fully secure a system. In the case of ZK, if you were to apply both, you could kind of have two scenarios. You maybe compile like a Rust program to using SP1 and generate a zero knowledge proof of that, plus run that in an enclave. If you do that, you really only protect against a programmer error in the underlying like SP1 library that you're using, for example. Because in the end, you're still like compiling the same Rust code. So if that Rust code that gets compiled to both the circuit and is run in the enclave has a bug, both will still like verify invalid data. So it's not like the end-all solution, but in the end, there's almost no defense against this. So I think right now, for most ZK-based protocols, like it's a good addition to require people to run, to do a multi-prover setup. The downside is, and I'm not as familiar with the hardware scene, but I think a lot of chip manufacturers has started to remove some features, so make access to TEs and enclaves less accessible. So if you're a big fan of being able to run a full node at home or on a Raspberry Pi and such, it's becoming harder and harder. And so if you're like a maximal like decentralist and really want anyone to be able to run it on any hardware, then pure ZK is still the solution.
It's actually the other way around. I mean, trusted execution environments is what most of the protocols use. And then you have, which is TE, and then you have TDX, trusted domain execution, where you can simply deploy or access the TE via Docker image. So we actually make it much simpler to integrate trusted execution environments for the tech stack. If this is what you were referring to, otherwise...
your CPU needs to have like Intel SGX or something like that on it, right? And
it all runs on this,
Yeah, and then correct me if I'm wrong, but I think the latest models don't have that anymore, and they've started to reserve that for like the enterprise CPUs. So if you want to run it at home or your home computer, I think it's harder to do now.
Yeah, you mean, okay, I know what you're referring to. Go ahead, the enterprise.
Yeah, exactly. But I mean, I think that's a good point that that might limit decentralization, and if that's what you're pushing for, that might not be the answer. I think what we've seen, since you talked about defense and military applications, for example, that we've seen actually increased interest on that front, specifically in purely cryptographic approaches. So purely cryptographic approaches combined with distributed systems, essentially, within those governmental organizations, to secure secrets, essentially, and run computations and have access control, and really have fallback systems, have redundancy, and reduce trust. I
think with regards to the cryptographic approach, it's possible to like for a certain algorithm have a formal proof that it is secure, right? And once and for all mathematically prove like this approach just works. You use a verifier for that or prover. And with hardware, like you can generate a checksum for hardware. You're constantly worried that some guy with like an electron microscope at home or a laboratory or something might find like a new vulnerability in it. So you can never truly prove that a chip is secure.
Yeah, and I think actually, and that might go into the direction of what you mentioned earlier with open source manufacturing and verification of hardware-based chips. I think there's even more problems associated. For example, if we had such a open source verification process, I think you would have to tear down the chip itself, because it's not just one single layer of fuses, but there's many layers, right? So you would require actual access to the hardware, and then there's the added question, okay, even if we wouldn't require to destruct such a chip, how could we verify that no tampering has occurred during the verification process?
Just,
Quantum mechanics.
yeah, and maybe
Exactly. Yeah, and but I mean, verification on the quantum scale. That's I think really also another question, right? So.
just to maybe introduce this to the audience, because we discussed this before the panel. We were talking about the elephant in the room when we talk about trusted execution environments, which is hardware, where we still trust actually the manufacturer, right? We have Intel, we have ARM, we have different hardware manufacturers that still have access to the root key. And if we talk about a chain of trust, we can maybe overcome these trust issues by implementing key management systems, by rotating or key hierarchies, right, of these hardwares and rotate it. But it doesn't overcome this main challenge. And that's why, of course, DK is not relying on this like trust issue. And we were discussing some ideas how to get rid of this, and there's actually a group of researchers that want to say, hey, how cool would it be if we can actually make these chips open source and verify based on not on economics or tokenomics, but based on physics and mathematics, that these chips are verifiable. So actually, I would also love to discuss this with you guys, with Automata afterwards, because Automata is a TE-based project here as well. But to bring this conversation back to the panel, just that everyone is aware of what we discussed here. I know you guys had these criticisms, and that's completely fair, but maybe what other opinions would you bring in? And maybe Supdoggie, you want to comment on this. What other ideas can we actually bring into research or are already applied to create a great multi-prover chain of trust?
So, just a quick comment on the verification of trusted execution environments, or where you have maybe an open source chip, but how can you verify an individual contributor is actually not maliciously altered this chip in some way where they can, maybe inspect the values of the circuit or whatever as it's operating. Is it possible to verify the operation of this chip? I don't want to go too off topic, but I do think that in our lifetime we may actually see the successful implementation of room temperature qubits or qubits, which is these quantum processor units, make their way into hardware, into consumer hardware. Right now it is not by any means accessible, but there is some research about actually being able to operate such devices at room temperature or with very small controlled superconducting components. In such a world, an idealized world, then you would have the absolute ability to verify that these circuits are operating without being read or modified in any way, because just the act of reading the value from the circuit would mutate its state, and it would not be verified. So that's just some fun food for thought, that quantum mechanics actually would solve this problem. It's not by any means ready, but there is research and development about this topic. The second part of your question was...
I mean, this is already good,
okay.
Because the question was more about what else can we implement to create a multi-prover chain of trust. I think that's a great answer. Yannik, you're smiling there.
I mean, my concern regarding this really is that you rather are painting this picture of within the next 5 years or something like that.
In our lifetime.
Yeah, I know. I think in your case it's different, but other people in this space paint this picture of, okay, in a few years we're gonna have these kinds of fully trustless hardware systems. So let's just use what's available right now, implement things, and at the end of the day we'll see data leak after data leak. So that's really my concern of building a system, especially with the distributed systems that we are building, that has this super high reliance on individual trusted entities that will fail. So that's really my concern with I guess good research. I think there's amazing research being done, but as you said, that will take significant amount of time and resources, and so we need to focus on a path forward. And I think that path might be the combination of different technologies, but it will almost definitely include distribution, right? And that's how at the end of the day we always all roads lead to MPC, at least in my head.
So I think it's interesting that you bring up this path of just getting there, right, or the means to an end, so to speak. With MPC, it is, yes, in an ideal world, it is very decentralized if you have a large network where you can guarantee that as long as you have maybe majority of consensus, then the network is secure. However, not everything can just start off with a very large set of trusted validators, and perhaps that in that transitionary stage, or in a multi-prover setup, you can reap the benefits of trusted execution environments because you can get away with a very small validator set to begin with, and as you grow larger, if you're combining the two with MPCs, then once you do get to a large enough validator set, so to speak, then you're
I think it really depends on the type of computation that you're executing, because if there's some party involved, as I said in the beginning, what we're working with is the dishonest majority trust assumption. So that means 1 out of n. If n is the size of your set of validators or computing parties, one has to behave honestly, so not be part of the malicious majority, right? If there's a setup where one can achieve relative zero trust by you being convinced to not be maliciously collaborating with the others, because I don't know, there's collaboration between competitors that train some machine learning model with competitors to get some shared intelligence without having to expose their individual data. I think that would be an example case of there being obvious skin in the game to not share your own data that you hold. So I think there's MPC setups where even with a super small set, you're able to have zero trust. Now in a fully distributed setting where you just want to outsource compute, I think you're right. You need a bigger set, a more diverse set, but that's also where cryptographic accountability protocols come into play. So the first accountability protocol that we, for example, have, that is for censorship, that forces nodes to actually run the computations, because many of those MPC protocols suffer from practical censorship limitations. In our case, we can identify non-participation and malicious participation, and with a proof then can punish that. And there's also other protocols. So for example, accountable threshold encryption. So to be able to, if there is some malicious decryption that doesn't happen according to protocol, so doesn't happen in a confidential way, there is a plain text value being revealed that essentially is a proof that states who collaborated to decrypt this value, right? And so in any case, if such a malicious operation has occurred, on some computer this plain text will exist and can be published as a proof to essentially flag that misbehavior has occurred. So I think there's many ways of reducing this remaining 1 out of n trust assumption even.
Great. Okay. Thank you for going much into detail here. No, I love this, but I think we want to wrap it up as well. I know we are keeping this to 20 minutes here. But last question, to bring it back to maybe close this deeper technical discussion, to give some more like applied use cases again, right? To say, okay, how do these different mechanisms impact the user experience, right? And if we say, you mentioned this already, like that for ZK, if we accelerate or have more scalability, we are at the same scalability that we can reach with off-chain TE execution. But how does it impact the user experience at the moment? And maybe what are you working on to enhance the user experience also? Closing question.
Yeah, so I think we've seen that people who build ZK-based protocols kind of suck at UX. I don't think ZK-based protocols fundamentally have to have bad UX. With provers being far more efficient now, you can do client-side proving. You can do that with Union, for example. You can actually generate one of the proofs that's necessary for bridging in your browser in probably about 20 seconds. We're looking to bring that down more significantly. Overall, I think both are like such backend technologies that fundamentally there doesn't need to be a UX difference at all between them. And I haven't seen them myself overall. I think fundamentally, like with the MPC setup, you always need to find additional parties to collaborate. So either you need like a network like Arcium, right, that's initially set up, or you need something else complicated to orchestrate. Well, with the ZK solution, you just have prover, verifier, and that is a very simple loop where not much can break, especially if the end user is the prover. then all they need to do is somehow generate that proof and get it to the chain or to the other party. And requires less orchestration on the network, less physical infra to operate. So it has a lot of advantages UX-wise. All that we need is better hardware, better code generation, and some improvements on the cryptography to make it almost seamless. And I think in maybe a year or two, a lot earlier than we'll see qubits in hardware, we'll see like proving technology that'll do like sub-second proofs, for example. And this age of like ZKPs taking a minute or 5 minutes or 10 minutes to generate will be fully gone. And we'll just see it as natural that you can generate a ZKP in like 100 milliseconds.
Supdoggie, what are your closing thoughts on this? Maybe from a TE perspective, but I think we're very, very advanced on that side already, right?
Yeah, sure. I mean, also, I mean, we didn't really talk much about FHE, but yeah, I mean, the FHE, I think would have, if we had an FHE person here, that would have been perfect because they could respond to everything we said here in a different way. But you know, as I showed earlier, like we're finding a way to apply that in a like a hybrid solution with trusted execution environments. In fact, I think MPC and ZK all have a place enhancing trusted execution environments. I don't think they necessarily need to be exclusive. In fact, when we start using ZKPs, even in secret contracts, we gain a lot more advantages. And you know, it's or the same is true with MPC. I think that my closing thoughts are that, yeah, I mean, combining approaches has its advantages and also its disadvantages. I mean, everything is a trade-off. I don't think ZKP is the end-all silver bullet by any means. Yeah, I mean, it's cool and it's exciting to see how the tech has evolved just in the last 5 years. ZKP has really done a lot in the last 5 years, and I'm excited to see where it goes in the next 5. So,
cool. Yannik, closing thoughts. Also, was the question about like how does the user experience gets impacted? Yeah.
Yeah. So I think what matters on that front is especially when offering generalized confidential computing that should be implemented in all kinds of applications, latency is highly important and the associated costs. So. We try to keep that as low as possible, and with this model that I outlined earlier, this computational model that we have on a cryptographic level, it brings us close enough and very close to plaintext execution time. So minimal overhead. I think what's also important is accessibility for this confidential computing power, I guess. So that's why with Arcium we really have this network that can just be accessed for confidential computing. You don't have to deploy a smart contract into Arcium. I think that's important, and that's a very conscious design decision that we took to just be this sort of supercomputer that you can access to run any kind of computation without having to worry about blockchains even.
Amazing. So very good user experience for any Web 2 and Web 3 developer. Great. I would like to close the panel discussion with this. I think we really touched deep on all the different cryptographic mechanisms. In the end, how we can actually combine all of them for a more sustainable multi-prover tech stack, right? This is, I think, what we are working towards in Web 3. I guess you all will stay around for a little bit. So please, if you guys have questions, we can't take them now here at the panel, but please take the speakers and ask them some questions outside. And thank you so much for joining.